Hello class, this is Ms. Augustine, and today we're going to practice doing a calorimetry problem. So here's the problem. In lab, a student placed a sample of an unknown metal with a mass of 89 grams that was at 100 degrees C into a calorimeter that contained 25 mils of water at 20 degrees C. After 3 minutes' time, the water and metal reached an equilibrium temperature of 35.5 degrees C. Now, the question is, what is the specific heat of the metal? Remembering that C for water, C being the specific heat, is 4.184 joules per gram degrees C. So this is just like the problem that we did in lab with the specific heat of a metal. We took a metal, we heated it in boiling water until it had reached 100 degrees C. We massed out our metal, and then we plunged it into a calorimeter. Remember, we used a styrofoam cup in a beaker as our calorimeter, and we plunged that into a known quantity of water at 20 degrees C, a known temperature, and then we let it equilibrate. We let it sit, and so it reaches a final temperature of 35.5 degrees C. So now we have to think about this. First off, always identify the variables. So starting with the metal, its mass is 89.0. The initial temperature was 100. The final temperature was 35.5, and remembering that delta T is always T2 minus T1, we end up with a delta T of 64.5. And 64.5 is a negative number because T2 is lower than T1. What does that mean? Well, we're solving for C, and what it means is that the metal lost heat. Its final temperature was lower than its initial temperature. Now let's discuss the water. Our water had a mass of 25 grams. How do we know that? We were given 25 mils of water. Well, because water has a density of 1 gram per milliliter. Our T1 was 20 degrees C, and then our T2 is the final highest temperature that it attained, which was 35.5. So the delta T is going to be T2 minus T1, which is 15.5. And again, here C is known because it's a constant, 4.184 joules per gram degrees C. Noticing that the temperature of the water went up, we can say that the water gained heat. So now, thinking about the calorimeter, it's a closed system, so we know that the heat lost by the metal is the same as the heat that was gained by the water. And let's also recall our equation for heat, Q, is equal to M times C times delta T, where M is our mass, C is specific heat capacity, and delta T is our change in temperature. So we could set this up as this Q for the metal is MC delta T. All of the subscripts here are referring to our metal. And on this side of the equation for water, again, Q is still equal to MC delta T, only in this case our subscripts are indicating that we're talking about water. So first we're going to calculate the heat that was gained by the water. Since we know all of the variables for the water, we can solve for Q. So again, bringing back our variables from the previous page, for water, M, T, T1, T2, delta T, and C. Now we're going to go and plug those into our equation to solve for Q. And again, our Q here plugging in for our mass, our specific heat for water, and our delta T allows us to cancel out our variables. Grams cancel out. Degrees C are going to cancel out, and that's going to give us a Q of 1,621.3 joules. So now we need to look at how many significant digits, and it looks like 3 significant digits, which will give us a Q of 1,620 joules. So now we can use the Q for water that we just calculated to calculate the specific heat C of the metal. Recalling that for the metal our variables were as follows: M 89.0 grams, T1 was 100, T2 was 35.5, delta T was negative 64.5 degrees C, and C is what we are solving for. And our Q is a negative 1620 joules. And remember I said that we could use the Q that we calculated for water. But you'll notice all of a sudden here we have a negative sign. And that's because the heat that was gained by the water was the same amount of heat that was lost by the metal. So Q for the metal is equal to negative Q for the water. So Q is equal to MC delta T. We're going to rearrange that equation to solve for our C. So C, the specific heat for the metal, is going to be Q over M delta T. Plugging in the numbers, again, the negative 1620 joules, 89 grams, and negative 64.5. Now you'll notice the heat was lost by the metal. There's a negative sign for delta T. There's a negative sign for our joules, and that means the two negative signs will cancel out and we'll get a positive value for specific heat capacity. Plugging it into the calculator, we get a lot of numbers, but recalling that we need to round to 3 significant digits. So our third significant digit is going to be the 2. So our C for the metal is going to be 0.282, and our unit, you'll notice, is joules per gram degree C. This is the typical type of calorimetry problem where you use something with known specific heat like water, and that allows you then to back calculate for the specific heat of an unknown, in this case a metal. I hope this helps, and look for more problem solving videos to follow.